Hello everyone, and welcome to part 2 of our study on room acoustics. Professor Fiore here to help you through. So last time we talked about what could happen with a sound wave when it hits a barrier, a wall, a window, a door. And we said there were three things. It could be reflected, it could be absorbed, it could be transmitted through. And we looked at the transmitted through part of that. In other words, sound transmission coefficient. Remember that? So what I want to do today is look at the reflected part. What does that do to the room? So let's begin by drawing a kind of a cheesy little room over here. And just imagine that this is a nice square room, or not square, rectangular. All right. I can't draw perfectly square. All right, so this is our room. All right, and in this room, there is a sound source. So let's just say that's a person speaking. Okay, and then over here, I have a receiver. And we'll just say that's a person listening. So this person speaks, and the sound emanates in all directions. All right, and the simplest thing that can happen is some of the sound goes directly to this individual. All right, we call that direct sound. Duh. However, sound could also hit the barriers. Now, we're only looking at sort of two dimensions on this, right? You know, the height we're not looking at, but this also exists. Remember this. So, you know, what else could happen is the sound could come off here, hit this wall, and remember, right, three things. Reflected, the sound can, just like a, you know, playing pool, the sound could be reflected and reach the listener. The sound could come off, you know, this wall as well. Bounce, reach the listener. It could come off, let's say the back wall. It could do something like this. And then bounce and reach the listener. It could, that's, you know, single bounces, right? Change colors over here. It could do multiple bounces. You know, we could get something like this. Come over here, bounce, bounce, bounce. You know, well, bounce, close enough, right? Those angles aren't perfect, but could have 2 bounces, 3 bounces, 5 bounces, and I'm only showing this in 2D. So, you know, we could have a sound that comes up, hits the ceiling, and then comes down to the listener. It could hit the floor and then bounce, because it's at an angle, or it could come out like this, hit the floor, and then bounce up and hit a wall, hit another wall, hit the ceiling, you know, hit another wall, and then hit the person, right? Boom, 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 boom. So this could get pretty complicated. But here's the thing to remember. At each one of these bounces, right? So here's a nice isolated bounce right here. What happens here? Those three things, right? Reflect, absorb, transmit through. So some of this energy is going to be lost from the reflection. In other words, only a portion actually gets reflected. Some of it's going to be lost. It's going to be absorbed, right? Turned into heat. Some of it's going to get escaped through this space. Okay? So before we were concerned about this stuff, you know, what happens to my next door neighbor? Now we're concerned about, well, what happens with the stuff that comes back into the room? All right? The surface that you have, the treatment of the surface and the construction of the surface will tell us a lot about the reflection versus the absorption. Right now, I don't really care about what gets transmitted through. What I really care about is, you know, how much of this gets bounced back in. So it's kind of the opposite way of looking at this. Now, a couple of things to note. Like we saw with the STC, the sound transmission class, how much sound gets reflected back is a function of frequency. It's not going to be the same at all frequencies. Now, there are some surfaces, you know, the classic one I always pull out is, you know, a painted cinder block wall, painted concrete wall. That's acoustically reflective. It's like a mirror. Stuff just bounces off that. Doesn't really matter what the frequency is for the most part. 98, 99% of the sound energy that hits it is going to be reflected right back into the room. Okay. Other things like, let's say, rigid fiberglass are really absorptive. Some things are very absorptive at certain frequencies, but not at others. An example of that would be the acoustic ceiling tiles, suspended ceiling tiles you often see. Those are good at absorbing frequencies in the, let's say, 1, 2, 3, 5 kilohertz range. So it helps with speech intelligibility, but they're not very good at absorbing anything down at, let's say, 100 hertz. Okay? So we've got this frequency issue going on. Another complication, or another thing to remember besides this frequency issue, are the path lengths. All right? So remember, sound has a speed of transmission, right? What's the velocity of sound? Anybody out there? Speak up. All right, so we're looking at, in U.S. customary units, maybe somewhere around 1,125 feet per second. All right, that's supposed to be an F. All right, feet per second, depending on what the temperature is. In metric, maybe about 343 meters per second. It is a function partly of temperature, but room temperature is somewhere around there. Okay, all right. Now, if you look at the little diagram I have here, the path lengths, right, the blue versus the green versus the sort of aqua teal, whatever you want to call it, those path lengths are different, meaning the amount of time it takes to get from the speaker to the listener changes. So this winds up creating something kind of interesting, this sort of sound field that you're getting. Now, when you turn these values into like a reciprocal, you say, well, how far can it go in a certain amount of time? 1,125 feet per second. Well, okay, a second's a long time. How long does it take to go a foot? Right? That's the other way of looking at it, sort of flip it upside down. Well, in 1 foot, it takes less than a millisecond. That's about 0.9 milliseconds. If we're looking at meters, well, a millisecond, you can go about 1/3 of a meter, right? So a meter will be traversed in about 3 milliseconds. So those are fairly short periods of time. But these path lengths can actually get kind of long. You think of a room like, let's say, a classroom, all right? You could be looking at dimensions out here, 20, 30 feet, okay? And then you start looking at bigger acoustic spaces. You think of like a theater or something. And now you're looking at, maybe 100 feet, right? Maybe more, all depending. And these delays can sort of add up. So I want to draw something a little bit different here. So I'm going to erase this. And what I want to do is consider the time delays that are occurring at the listener. All right, so this is time on this axis. And up here would be an SPL, sort of a short period SPL. So I want you to imagine that we're just going to produce a click, right? I might get like a dog clicker, something like that, or I might slap 2 pieces of wood together, and I just get this very sudden, snap kind of noise. All right, so that's my original sound, and I'll just put that at time. Oops, that was kind of ugly. That's my initial impulse over here. So I just want to put this right next to it. So there's my initial impulse. That's 100%. Now, there's that one direct sound ray. So let's say that person is sitting, 10 feet away. I'll do customary US units for this. So he's sitting 10 feet away. Well, that's going to take a little less than 10 milliseconds, about 9 milliseconds, for the sound to reach them. Right? There's going to be very little attenuation. And I'm just going to draw that as a spike, right? So this is just this snapping noise that I've produced, right? And then we have some of those other things. We have like the single bounces, off the sidewall, off the floor, off the ceiling, off the back wall. Okay. Those have a longer path length. They're going to take a little longer. And when they hit the other wall or the floor, they're going to lose some of the energy. So those things are going to take a little longer to reach, and they're not going to be quite as big. You might see something like this. I'll just stick one in here. And I wish I could draw this a little better, but these are supposed to be just straight up and down, right? Okay, so, these are like these, like I said, side wall, back wall, front wall, the floor, the ceiling, things like that. These as a group are referred to as early reflections. Pretty obvious name. Right? As distinguished from the direct sound. All right, so we have this one direct ray. All right. Then we have these things that have, 2, 3, 4, 5 kind of bounces. And with those, with more bounces, we lose more energy. And there's more possibilities. When you start bouncing more and more and more and more, there's more and more ways to sort of get to the listener. So these things start to become closer and closer together. But like I said, they're lower in amplitude. And it all depends on what they hit. You have maybe some surfaces are highly absorptive. So that thing comes back at a fairly low amplitude. Some of them a bit bigger. But, these become more and more frequent, like I said. And, and they keep getting smaller and smaller and smaller and smaller. Okay? They sort of trail out here. And like I said, every now and then you might get a big one or a relatively large one. But pretty soon this all blurs together and you just have, this sort of background kind of sort of fuzz. All right? So these are your late reflections. Now, all of these reflections together create something that we call the reverberant signature. This is all reverberant energy. And you don't really get this outside. If you're outside, you might get a random reflection off the ground, off a nearby building, something like that. But you don't get this kind of thing. Think about being in a classroom. Not only do you get reflections off the walls, you get reflections off the chair in front of you, the table next to you, off of a person sitting next to you. You get lots and lots of these sorts of things, all right? So you don't really get the same kind of reverberant experience, if you're standing outside in a field. Right? There are places you could go where there's a lot of reverberant energy. If you stood at the mouth of a cave, let's say, a lot of energy is going to bounce around inside the cave. Very reflective. Rock is really good at reflecting sound. All right. In any case, we can kind of come up with an average on this, an envelope. What does this thing follow? Okay. And what we do, taking this average, we measure down so that we're down 60 decibels from the original value. Okay. And actually, I'm not really drawing this to a great scale here. In most rooms, this would be, well, I don't have enough space, but it would be way the heck down here somewhere. But whatever this time is, that is called the RT60. It is the reverb time of the room. Now, basically, the longer the reverb time, the more lush kind of a sound that you get, right? So if you walk into, think of like a cave. Think of maybe a basement that doesn't have anything in it. It's just concrete walls. Or for that matter, think of like a large, maybe a bathroom that's all tiled. There's nothing, there's no like shower curtains or anything. It's just all, hard surfaces. And you get this sort of very full, lush kind of sound. That's the reverb. It's all of this stuff, right? It's all of this stuff together, right? That gives you the signature. The longer the reverb time is, the greater this effect, essentially. Because when you compare rooms, essentially reverb time increases with two things. It increases with the size of the room, the volume of the room. Bigger rooms have longer reverb times. Why? Well, things are farther apart. So the path length to get back to the listener is that much longer, right? So all of these things kind of spread out. The early reflections are going to be like way out to here. And then you get the late reflections. So the whole curve winds up, stretching out like this. And the reverb time goes, way the heck out here. The other thing is the kind of materials you have, the absorption of those materials. If you have highly absorptive surfaces, then the reverb time is shorter, right? If you don't, boom, you get really long reverb time. So if you think of a space that's physically very large and has very hard surfaces, you get really long reverb times. So I'm thinking in terms of maybe a large auditorium, like a sports auditorium where you might play hockey. Lots of concrete, very large volume. You get these really long reverb times. It's hard to hear someone speaking, that's not that far away. I mean, it can be a real challenge, for example, to hear everything clearly from an announcer, right? Sometimes, they'll have graduation ceremonies and concerts and things like that and those kinds of structures. And the sound is just very muddled. Right? It's not the best place, acoustically speaking, to have, let's say, a concert or some kind of presentation like that. Right? That's not what it's designed for. Whereas a concert hall, it might have a large volume, but if it's properly designed, we're going to be looking at the absorption of the materials, and we're going to try to control that RT60. Right? In your own experience in a home, you might have a larger room, let's say a living room, and you're going to pull all the furniture out of there because maybe you want to paint it, or you're going to put a hardwood floor in or something like that. You notice when you walk into that room, it doesn't sound the same. It's got that sort of empty, cavernous sound. That's because the RT60 has increased. It's not just the surfaces, it's the things in there. So in your living room, you would have maybe large upholstered furniture, chairs and couches, sofa, things like that. You might have heavy drapes on the windows, things of that nature. All of those are going to absorb sound, and they're going to reduce the reverb time. They're going to decrease that RT60. All right? You take it out, there's nothing to absorb. The sound just bounces. So a larger and larger percent of the sound that hits the wall or the floor or the ceiling, a larger percent of that can just come back into the room and bounce again, right? And you get more and more of these reflections. Whereas if there was, all this furniture and so forth, a big thick rug, something like that, a smaller percentage comes back in, so those late reflections are all reduced in amplitude. The RT60 shortens up. So you might have an RT60 that's, a fraction of a second in a small room, maybe a second or two in a larger room. But then you get into these large spaces with large, hard surfaces, you get reverb times of many seconds, 5 seconds, 10 seconds. These things can be crazy long. And it just, like I said, it makes it very difficult to discern acoustically something like a conversation or, a musical piece or something along that line. So we have to be very careful with that, right? The construction of the acoustic space. You want to make sure that the acoustic space is appropriate for its use. If your use is to watch people play hockey, that's entirely different than, going to watch a concert, all right? Okay, so this sort of gives us a clue into, why when you walk into the bathroom or you walk into an empty room, it has this sort of odd kind of sound. And interestingly enough, we kind of like this sound in music to an extent. We very often put it in artificially. In other words, in some recording studios, we record musical instruments or voices in what we call dry form, in a space where there's not a lot of natural reverb, and then we add it on artificially later. Right? So we have the computational techniques now that we can simulate an acoustical space and sort of apply that to the sound, right? And it sounds like this person is in a cathedral, or it sounds like this person is in a, a very live room that's, wood paneling and a hardwood floor and things like that, all right? And quite literally, we can come into spaces now, right? This was not done, back in the 60s and 70s. If you wanted a live sound, what they very often would do is just feed the sound through a loudspeaker into what was called a live room, like an all concrete room. And, have a microphone in there, and they would pick up the sound and mix that back in with the original sound, and that's how they would get reverb. Or they would have electromechanical means. Guitar players had, reverb amplifiers that had little mechanical springs that would vibrate and would simulate this kind of effect. But now with computers, we can literally go into an acoustic space and produce this sort of click that I was talking about initially, and then record this. We can literally record this, and then there's mathematical techniques we can use, essentially something called convolution, to apply this to, let's say, a vocalist's track, right, a vocal track, and bingo, now it sounds like that person is in that acoustic space. They're in that cathedral. They're in that room, whatever it was. We control that with great precision, if we so desire. All right, that's kind of cool. So you can, literally record something in your bedroom, small room, and make it sound like you're in the middle of a cave. Okay, cool. All right. So stay tuned for the next part. We're going to look a little bit more at these room acoustics. Until then, take care.